7 minutes is all Mars gives you, and for more than half the spacecraft ever sent to land there, 7 minutes was all it took to fail. By the time engineers on Earth hear whether the landing worked, the spacecraft has already been sitting on the surface, or scattered across it, for 11 minutes. The window cannot be extended, no command can be sent in time, and the sequence cannot be paused. Every step fires automatically, in order, trusting the calculations of people who will not know if they were right until long after it matters. 6 out of the first 9 attempts to land something on Mars ended in wreckage. That is not a streak of bad luck. That is a mortality rate. And the physics responsible for every one of those failures has not changed by a single variable. The same trap that killed the earliest landers is waiting, unchanged, for the next one. What makes this worse is where the trap comes from, not from space being too hostile, but from Mars being almost hospitable. Almost. Mars has an atmosphere. That sounds like good news. On Earth, an atmosphere is what lets you land a plane, open a parachute, slow a falling object to survivable speed. The atmosphere is your friend. On Mars, the atmosphere is just thick enough to set your spacecraft on fire and just thin enough to refuse to catch it. It does both things at once. It heats the spacecraft to a temperature hotter than a steel foundry during the descent, hot enough that unprotected metal would melt before it reached the ground. And then, after doing all that heating, it still leaves the spacecraft moving faster than a Formula One car at full speed when it hits the surface. Friction destroys you from heat, gravity still kills you on impact. The atmosphere does neither job completely. It just makes both problems worse. This is the core problem that every Mars landing system has ever been designed to solve. The heat shield handles the fire, the parachute slows the fall, the retro rockets handle what the parachute cannot, the landing legs or airbags absorb the impact. Every solution adds weight, every solution adds complexity, and every solution creates a new way to fail, because every solution must trigger at exactly the right moment in a sequence that no human on Earth is controlling in real time. Here is where most people's instinct breaks down. The common assumption, the movie logic version of this, is that getting through the heat is the hard part. Survive the fire and the landing is basically done. The parachute opens, the spacecraft drifts down, the legs touch the ground. That instinct is wrong. The parachute is not a solution. The parachute is a delay tactic. It buys seconds, not enough seconds to land safely, but just enough seconds to trigger the next system in the chain. The chain has 7 steps. Every step depends on the previous one succeeding. And each step has a timing window measured not in minutes, but in fractions of seconds. Stop here. You are the engineer who programmed the heat shield release timing. Your data says fire the release at 3 minutes and 42 seconds into the descent sequence. Your colleague's calculation says 3 minutes and 38 seconds. Both of you ran the same model. The mission launches in 1 hour. There is no time to retest. The spacecraft will be moving at nearly 20 times the speed of a rifle bullet when this decision executes. Release the shield too early, and the heat burns through the lander before the parachute has time to work. Release it too late, and the shield blocks the parachute and it never fully opens. Either way, the spacecraft hits the ground at lethal speed, and you find out which one of you was right 11 minutes after it already happened. Which number do you commit to? Think about it. The real engineers had to answer that question. We will come back to what they chose. The timing margin throughout the landing sequence is brutal. The retro rockets, the last set of engines that slow the spacecraft for final touchdown, must ignite within less than 2 seconds of their target window. 2 seconds sounds forgiving until you understand what it means in practice. Fighter pilots, among the fastest human decision-makers alive, need at least half a second just to consciously react to something they already see coming. 2 seconds is the total margin for an automated system, executing on calculations written months before the mission launched, on a spacecraft moving faster than any human reflex can track, with a signal delay that makes real-time correction physically impossible. This is not a case where a fast operator could catch the error. There is no operator. There is only the pre-programmed sequence, trusting the judgment of engineers who are currently sitting in a room on Earth, watching a timer tick, unable to do anything. Now, think about your own decision from earlier. You committed to either 3 minutes 42 or 3 minutes 38. That choice is sitting in the spacecraft's computer right now, locked in, unchangeable. How confident are you in a calculation you made under pressure months ago that you cannot correct? The real engineers were not confident, they were methodical. Confidence is for systems you can adjust. Pre-programmed landing sequences require something harder, the acceptance that you will not know if you are right until it is already irreversible. 6 missions failed. Not all of them failed at the same step. Some burned up because the heat shield failed or the geometry of atmospheric entry was wrong by a fraction of a degree. Some survived the heat in the parachute phase and then hit the ground too fast because a retro rocket did not fire. One mission lost contact during descent and was never heard from again, the exact step of failure unknown, which is its own kind of horror. The sequence has 7 links. The chain broke at different links on different missions. That is what a failure rate looks like when the problem is genuinely hard, not one consistent flaw, but cascading vulnerability across the whole sequence. The engineers who built the Curiosity rover faced a version of this problem that had no clean solution. The rover was too heavy to land with conventional legs or airbags. The impact speed, even after heat shield and parachute, would have destroyed the science instruments. The options were remove science instruments to reduce weight and use a simpler landing system, or keep all instruments and build a landing system that had never been tested on Mars. Option 1 meant a partial mission. Option 2 meant a rocket-powered hovering platform called a sky crane that would lower the rover on cables from above, hold position against Mars gravity using thrusters, release the rover when it touched down, and then fly away and crash deliberately into the surface at a safe distance. Some of the engineers who built it called it insane. They were not wrong. It was insane. It also worked. Twice. The sky crane descended, held position, lowered the rover, and then, having completed its only purpose, flew off and smashed itself into the ground a few hundred meters away. Success announced by controlled crash. Congratulations, the most complex landing system ever sent to Mars just destroyed itself on purpose, and that counts as a flawless mission outcome. Before you decide the sky crane proves that complexity wins, consider the cost of that decision. Every additional system in the sequence is another link in the chain. The sky crane worked twice because the pre-programming was right, the sensors hit their targets, and nothing in the chain failed. Not because complexity is safe. Because complexity was the only option the physics left available, and it happened to be executed without error. The missions that failed were not simpler because their engineers were less capable. They were simpler because simpler was what the engineers had, and simpler still killed them. Here is the principle that every Mars landing, every failed mission, and every successful one confirms. A system that requires perfect sequential timing, where each step depends completely on the previous one, fails at its weakest link, not its strongest. You do not get credit for the 6 steps that worked if the 7th one doesn't. This is not specific to Mars. It applies to surgical procedures with preset instrument sequences. It applies to nuclear plant emergency shutdowns that execute in automated cascades. It applies to any engineered solution complex enough to solve a nearly impossible problem. The more steps in the chain, the more ways it breaks. Mars is simply the most unforgiving classroom for that lesson, because the test happens 11 minutes before the grade arrives and there are no retakes. The physics has not changed. The window is still 7 minutes, and the next mission will find out what the engineers got right and what they got wrong, the same way every mission before it did, after it is already over.